Yeah, you need to share your screen or whatever. Sure. Okay, good evening, everyone. Welcome once again to Amateur Astronomers Incorporated, and my name is Mary for another one of our presentations. We had a little late start tonight, but hopefully you can join in. We make our home here at Sperry Observatory in Cranford, New Jersey. I'd like to introduce to you our member, Max Watzky. He's been a longtime member now of AAI. He just graduated from high school, and he has been given many presentations here at Sperry Observatory. So with that, Max, I'm going to turn it over to you.
Hi. Thank you. It is so nice to be with you all. Is this loud enough? Can you all hear me?
Yeah, a little louder.
A little louder? I'll speak a little louder too. Is this good? Perfect.
Yeah, a little more.
A little more? Okay. Is that good?
Yes.
I don't know where the speaker is. All right. Hi. It is so nice to be with you tonight to talk about a little bit of the research work I've been doing over the last couple months. This project, which I gave the fancy title Deep Learning in Deep Space, began as one of my high school graduation requirements. Since my school requires that all students, before they graduate, do a month of independent study or research. But in the time since, I really sort of fell in love with it and have continued to improve and polish the results. So the project that I did, as the title hints at, I guess, was focused on the intersection between astronomy and computer science. And more specifically, I wanted to start digging into the question of how astronomers use computing tools for their research. So for the first part of the project, I learned. I watched videos, I listened to lectures, I read articles and books. And for the second part, I implemented what I'd learned in a series of small coding projects. My focus was mainly in two areas. The first is AI, which has a number of important applications in the way we process and analyze astronomical data. We can use it to classify different types of objects in astronomical images. So if you want to discern what type of galaxy is or what type of star is, or even detect a transient event like a supernova or an asteroid that might go undetected to the untrained eye. We can also use AI to remove noise from astronomical images, which can help pick out real starlight from other junk-like artifacts from the camera. Like in this example here, where we have a spiral galaxy, which is shown in infrared. And in this original image, there's a ton of noise, and in this one processed by AI, there's almost none. The second area I looked at were simulations of physics. Simulations are the closest thing that astronomers have to lab experiments. They enable us to test hypotheses about different phenomena at every scale, from the level of planets to the level of galaxies in the entire universe. So let's start with AI. AI is kind of like a scary buzzword that's been thrown around a lot recently, thanks to the rise of ChatGPT and other products like it. And when I tell you I've been learning about AI in space, you might think I'm talking about this. But I think when you get down to it, the reality of AI is a lot less scary. At their core, most AIs we talk about today, like ChatGPT or self-driving cars, you name it, are based on some kind of neural network, which is really just a mathematical architecture, which is modeled after the structure of neurons in the human brain. The brain is composed of billions of neurons, each of which processes inputs and spits out outputs. Neurons receive signals from other neurons through their dendrites. And if enough input signal is received, then they can fire an output along their axon, which can then be transmitted to other neurons. Neurons in the brain can't do anything on their own, but together, they can form networks that are capable of performing complex tasks. For example, there's a network of neurons in your brain that process images coming in from your eyes and can classify what you're looking at. The analog for the neuron in an artificial neural network is what's called a node, but you can call it a neuron as well, which also has the capability to take in inputs like the dendrites, process them, and then return an output like the axon. By connecting together these nodes into a bigger network, we can then model more complex structures. In the brain, neural networks learn by strengthening and pruning away the connections between the neurons. The pathways that get used more often might become stronger, while the pathways that don't get used as often will be pruned away. In an artificial neural network, we can emulate this by doing essentially the same thing, adjusting the strength of certain connections and nodes in the network in a process called training. Let's say we have a very simple neural network composed of just two layers. We have an input layer, which takes in the brightness of different pixels in this image. Let's say this one node corresponds to that one pixel. And we have this output layer, which is just one node. Let's say that if this node fires, it means there's a dog in the image, and if it doesn't fire, there's a cat. We can control how the network works using a set of values which control the strength of the different nodes and connections, which is just like that process of strengthening or pruning away different connections in the brain. The values that affect the strength of the nodes themselves are called the biases, and the values that control the connections are called the weights. We can sort of imagine these like dials or scales, which can be fine-tuned to make the network do different things. For example, if we increase the bias of this node, it means it'll send a stronger signal along here. This node will be more likely to fire, and the network will be more likely to say, this is a dog. At first, all the biases and weights, all the little dials that control the network are set randomly. So the network doesn't really behave correctly. Here it's saying this is a cat. But the key is that we know it's a dog, and we can calculate how each of those little dials, each of those weights and biases need to be shifted in order to correct the output, in order to make this say dog. This process is called backpropagation, if you ever read like a neural network paper or whatever, because we're going back through each layer of the network, calculating how the different weights and biases affect the output. So here with only two layers, it's a pretty simple process. Maybe in order for this to say dog, we want to strengthen this connection, or we want to strengthen this node here, for example. We can then nudge the network a little bit in that direction. We can look at how we need to turn the dials and turn them just a little bit. And this makes it just a little bit better at the task. If we repeat this process, maybe hundreds or thousands of times, showing the network more and more images of cats and dogs, it'll eventually learn how to classify them on its own. Now, this is a pretty small, simple neural network, but we can change it to do more complex things. Maybe instead of the input being an image and the output being a classification, dog or cat, we can make the inputs the sensors from a car and the output drive left, right, forward, or backwards. Or like ChatGPT, maybe the input is a question and the output is a really snarky answer. These tasks may have seemed impossible for a computer only a few decades ago, but thanks to neural networks, they're suddenly a lot more manageable. So my ultimate goal with this part of the project was to make a neural network from scratch and use it to perform a few sample tasks in astronomy image processing, like removing noise. From start to finish, the whole thing took about a week, and it totaled about 600 lines of Python code. I thought this would be like readable, but it's really like not. I won't bore you with all the specifics of it now, but if anyone is interested in looking at the code, I have it here, and I'm happy to provide more details about it later. The summary is that the program allows a user to create a new neural network by providing the number of nodes and layers, and then train it with a set of data. You need a set of input data, which is what's actually getting fed into the network, and then you need a set of predicted classifications, what the network should be outputting. And using that, the network can train itself. So I didn't just like take it at its word. I wanted to test the network to make sure it was all working properly. The first test I did was really simple. I made a network with two inputs, some processing in the middle, and one output. The two inputs you can imagine as being like an X and a Y value on the plane, and the output is like a color, blue or red. And what I wanted to do was train the network to figure out where a circle was. So red should be inside the circle and blue should be outside the circle. And this kind of spoils it, but after training, it was able to do this pretty well and learn where the circle was. So that's pretty simple. The next task I did was a little more complicated. So instead of two inputs, I scaled the network up to take in 784 inputs, one for every pixel of this image. The images I used are from a very famous AI dataset called the MNIST dataset, which is a bunch of pictures of handwritten digits. This one's a 5. And the goal was to train the network to identify what number was written in the image. This task might seem trivial for us, but for decades, this proved extremely hard for computers. Imagine designing some code on your own that could do this for any number from 0 to 9 in any place in the image. So after training, the network was able to do this pretty well. Here it's saying there's a 93% chance this is a 5, although it's a little unsure. Maybe it could be an 8. I see where it's coming from. So even though the network was classifying those images correctly, I wasn't sure if it was actually capable of learning about the key features of the image. Maybe it's just memorizing certain pixels and corresponding them with certain numbers. To test this, I trained the neural network to make reconstructions of images. So rather than classify them, I just wanted the neural network to spit the same thing out that it was seeing at the beginning. However, to prevent the neural network from cheating and just memorizing pixels, I forced it to pass its information through this bottleneck. So it takes in 784 pixels, but it's forced to condense everything down into only 64 nodes in the middle, so only less than 1/10 of the original size. So this way, the network is forced to aggregate certain pixels together in its understanding and hopefully start to see patterns like lines and loops in the numbers. The result is pretty remarkable. Not only can the neural network reconstruct the image, here's the original, here's the reconstruction, but it can also reduce noise. It copies over only the real features that it's learned while ignoring any junk that might have come with the image. This structure of a neural network with a bottleneck in the middle is called an autoencoder, and it's one of the main tools that astronomers use to remove noise from their images. So now that I had this functioning autoencoder network, I set out to do some actual astronomy work with it. The images I was using came from what's called the Galaxies Zoo dataset, which is a collection of color images of different galaxies, spiral, elliptical, and irregular. The full dataset contains millions of images, but this was way too much to put on my hard drive, so I decided to work with only 10,000. After training on them for about 20 minutes, the network had parsed through all of them, and it was able to do a pretty good job of learning the key features that make up a galaxy. Here are some of the results. In the top row, we have some of the original images from the data set. You can see there's quite a bit of artifacting and noise. I'm not sure if that comes from the camera or from sort of like compression that happened along the way of downloading them. And in the bottom row, you have the reconstructions that the network has produced. In almost every case, the noise is dramatically reduced. You don't see any of this strange artifacting, although sometimes this comes at the expense of the fine details. Like in this middle image, you can see pretty clearly in the original, it's supposed to be a spiral galaxy, but in the end, you kind of end up with this amorphous blob. Although in other cases, like the second one from the left, the image is preserved almost perfectly, and it even looks a little bit clearer. So I mark this a success. So, all right, on to the second topic, which are simulations of physics. So modern astronomical simulations that run on giant supercomputers take into account all sorts of things like magnetic forces and fluid dynamics. But the most important thing to simulate is gravity. Luckily, it's pretty simple. If you want to measure the gravity between two masses, it's just the product of those two masses divided by the distance between them squared, and then you adjust it by this factor g, which is just going to help our units come out nicely. For big masses and large distances, relativity screws with this a little bit, but this is an almost perfect approximation for most cases. In the real world, gravity acts continuously at every instant. But since we don't have infinite computing power, we're going to measure gravity at a defined time step, maybe like every second or so. And we're going to call that delta t. So if we know the force on a particle thanks to gravity, we can figure out its acceleration from Newton's laws. All speed is acceleration over time, and all distance is speed over time. So if we can find the acceleration at different points, we can chart out the position of our planets or particles at different times. So we run our simulation over a certain number of time steps. We collect the positions of the particles at all those steps, and then we're able to make an animation like this. This is the basic process of what's called numerical integration, which is taking like an acceleration or a force and integrating it over time. And it's the foundation for most astronomical simulations. So when you have only two particles or bodies in a system, that system is stable. Those two bodies will travel the same path over and over and over again. Think of like the Earth and the Sun. you can pretty much exactly predict where the Earth is going to be in its orbit, because the only thing influencing it basically in our local sphere is the sun. In fact, in some of these systems, there's no need to use numerical integration. You can predict the exact path of the particles using just Kepler's laws. But as soon as you throw in a third body or a fourth or a fifth, the system becomes chaotic. You can no longer predict it. And so you need a tool like numerical integration to figure out where things are going to be. So to demonstrate this, this is my second little coding project. I built a little interactive, I hope the people on Zoom can see this. So we start off with blank space. And if you click, you can create a planet. So the program is running, but the planet isn't doing anything because it's not experiencing gravity from anything else. But as soon as you create another planet, they're attracted to each other. There's no collisions in this, so they just pass right through each other. But this shows the principle from before, that when you have two bodies, they're basically just going to follow the same path over and over again, and you can predict pretty much exactly where they're going to be. But as soon as you throw in a third body, things start to become chaotic, and you can't really predict what's going to happen. So in this case, those two planets seem to have gone off and made friends with each other, and this third one is left on its lonesome. But we can make some friends for it. And so, yeah, it's almost impossible to predict what's going to happen. It's pretty chaotic. This simulation runs pretty smoothly. It looks pretty fast with only a few bodies. But if you start adding more and more and more, it'll slow down really, really quickly. And the reason for that, if I get back to my slides, is that in the simulation, you're computing gravity between every single pair of objects. So you're looking at the gravity that every object exerts on every other object in the simulation. And what this means is that if you have 10 bodies, you have to calculate the effect of those 10 bodies on the 9 other bodies. So you're doing basically 10 times 10 calculations. So if you have n bodies or planets in your simulation, you're doing n squared calculations. If you have 10 bodies, that means 100 calculations. 100 bodies, that means 10,000 calculations. And if you have 1,000 bodies, which isn't even that many, you're doing 1,000,000 calculations every time you want to do one more step in your simulation. So that's going to slow things down a ton, especially as you increase the particle count to look at more and more complex systems like galaxies. And the reason this is inefficient is because we're not doing it in the way that you would naturally look at gravity. Let's say you want to calculate the gravity that the Andromeda galaxy exerts on planet Earth. The way you wouldn't do it is add up the gravity from every single star in the Andromeda galaxy. Instead, you'd treat Andromeda as acting from one single point and calculate the gravity from there.
Makes sense.
This is the intuition for one of the main optimizations for this kind of simulation, which is called the Barnes-Hutt algorithm. It was named after the two guys who invented it, Josh Barnes and Piet Hutt. I think Piet Hutt is still a professor at Princeton. I might send this to him. I don't know if he's interested. They invented it in 1986, and the main idea is that it lets you group bodies together in your calculations. So what the algorithm does is it recursively divides up the space of your simulation into quadrants. So we take this space, divide it up into 4 pieces, divide each of those pieces into 4 pieces, and so on, until each body lives in its own piece. And what this lets you do is very easily group bodies together. So let's say you want to calculate the force on this particle from all these particles. You can say they're far enough away that we can just approximate it, stick them all together in this one big box, and calculate the force easily. And what this does is it reduces the number of operations you have to do if you have n planets from n squared down to n log n. So let's say you have 1,000 bodies. Instead of doing 1,000,000 calculations, you're doing maybe 5,000 or 10,000. So a pretty dramatic speed up. So what I wanted to do for this part of the project was actually make my own version of this algorithm. I started by trying to program this in Python, and that turned out to be a mistake. Python is a pretty slow programming language, and the reason that is because it's interpreted. The computer is trying to run every single instruction in the code as soon as you run it, instead of giving itself a chance to compile things beforehand and make the process more efficient. That's the basic explanation, I guess. And that slows things down by a ton. So when you're talking about thousands or millions of particles that are interacting with each other, the entire thing grinds to a halt. The other issue I was running into was with collisions, when two particles get really, really close to each other. The problem is that when you take our gravity equation from before, the two masses multiplied together divided by the distance between them squared, if the distance goes to 0, then the force goes up to infinity. So if you have two particles here that are really close to each other, they're going to experience like an absurd amount of force towards one another, which, as you saw, in my thing before, causes them to pass through each other and out into space. This isn't a problem in real life because gravity is acting continuously. So as soon as they're past each other, the force is tugging them back together again. But if you have a finite time step, let's say it's 5 seconds, in those 5 seconds, maybe the two particles can get 1 billion miles away from each other and they're gone. So there's a quick little fix for that that I looked into, and it's adding this little term here in the gravity equation. It's probably really tiny. It's like 0.1 or 0.001 or something like that. And what it does is it means that at any reasonable value of r, like 1 meter upwards, basically, it has no effect. It doesn't change the calculation. But when r gets really, really small, it limits the amount that f can increase. So instead of going to infinity, maybe it goes to just a regular old high number. And that prevents the particles from flinging each other off into space. This seems like a pretty small issue, but it was like plaguing me. I fixed the issue with Python by reprogramming the entire thing in Java, which sped things up considerably because Java is a compiled language. So the computer gets a chance to make its instructions more efficient before everything runs. The final product could handle more than 1 million particles on my little laptop, and it works in both 2D and 3D, although I ran most things in 2D since it was a lot faster. So I made 3 simulations to show you what this kind of algorithm can do. Each of them was with over 100,000 particles and took a few hours to run on my laptop, which isn't actually that absurd, but it was a pretty decent time investment. So here's the first one. The people who were on the research email list have probably seen this already, since I've been like spamming them with this. So what we start off with is a bunch of particles in a disk. They're denser towards the center, and they all have some velocity around the center. And if I hit play, you can see that they'll very quickly start forming into some interesting structures. Sorry for the lag on the video. The resolution here isn't that great, so you can't see it perfectly. But what's happening is that you're ending up with these ring structures and spiral arms that are getting formed. And eventually you have a shape which is basically the same as a spiral galaxy. There was one little problem. Well, there were a lot of problems with the way I coded this, but one big problem is that when particles leave a certain bounding box that the simulation is on, they disappear forever. And that just happened for a bunch of particles in that spiral arm up there. They all disappeared. So now the whole thing is a little bit bottom heavy, and the galaxy is going to start moving downwards, which it probably shouldn't be doing. But anyways. So that was the first big simulation I did. So I figured one galaxy is cool. Why not do 2? That's a weird bug. And the sort of scientific reason for checking this one out, it's 2 galaxies this time, was that I wanted to test this theory, which is the predominant theory, it has been for the last few decades, that when you stick 2 spiral galaxies together, they won't form into another spiral galaxy, they'll form into a blobby elliptical galaxy. So I can run the video and show you how that turned out. So actually, let me slow this down because this is really fast. So we have our two galaxies. They start as those disks like before, but they very quickly form up into these sort of spiral patterns. They collide, and this is kind of cool. They don't actually stick together on the first collision. They sort of pass through each other. And you have these weird sort of spindles that form, which kind of reminds me of what a cell looks like when it's dividing in mitosis. And the result is indeed a big blobby elliptical galaxy. It's not another spiral. Although the entire thing still has all of its angular momentum from before, so it is still spinning. Oh, I didn't mean to do that. The last simulation I did, I wasn't exactly sure beforehand how it would go. I started with a big square. I filled the entire simulation space with a bunch of particles, and they don't have any initial velocity, so they're all just attracted to one another. And the idea here was to see if I could maybe make them all collapse together in like a Big Bang style thing, and then see what happens from there. So let me slow it down to a reasonable speed. And you can see what happened. So the entire thing does sort of collapse together, although it doesn't collapse to a point. It sort of collapses to a smaller square. And then you have these sort of four bundles of density that kind of form. Although those sort of combine up here to form into this giant kind of galaxy cluster type shape. And then you have another one down here on the bottom. And then over time, these still are acting under the influence of gravity. The two big galaxy clusters combine and form into one big one. All right. Those are the results of my project. Thank you. Oh, wait, let me. Please let me get my finish slide. Thank you.
Anybody have any questions?
Yeah.
I do.
Yeah.
Excellent job.
Thank you.
Two things. How are you going to verify that you didn't put any bias into the code? And also verify your results.
So for the simulation bit?
Yeah. So when you build on that, and you said you only did that with 600 lines?
So, oh, the neural network, hold on, let me go back. This thing was 600 lines, yeah. The code for the simulation was probably like 2,000. It was a lot longer. So the way I structured it was that I had like a, it's like coding terminology. I'm really sorry in advance. I had a class which represented this structure, which is called the quad tree, which is like the structure of the different quadrants within quadrants. There's a function that places all of the particles into the tree, and then there's a function that calculates all the forces on them, and then there's a function that takes those forces and calculates the acceleration and the velocity and the position over time. And then I wrote a bunch of other like helper functions that create different starting scenarios, like the circle that forms the galaxy and the box from before. And I guess there is kind of bias. So the way that I came up with this initial configuration for this galaxy at the beginning was that I read a paper about the mass distribution of particles in a spiral galaxy like the Milky Way, and I found that it followed this exponential distribution where you have a lot more mass in the center. So I figured I'd start it like that. Although I imagine if you start it in a disk that's uniform, you'd probably end up with a similar result. A lot of the mass would fall inwards, and you'd have a sort of similar situation. Yeah.
Do you have any something else where I can find more about what you made the presentation about?
Yeah, so there's a few articles that I read that informed basically like everything I did. Like there was this great article by a mathematician who I think his internet name is like 3 Blue 1 Brown, and he has an amazing series on how neural networks work that have basically like inspired me in all of this. And then I have a couple articles that were really nice on simulations that I'd be happy to show you.
Thank you.
Yeah.
You did good.
Thank you.
Your final simulation that you showed us.
Yeah.
You'll get the same result every time.
So if you, okay, so the way the particles start in the beginning are random. So you have a random square. So if you ran this code again, you would get a different result because of the butterfly effect. The butterfly effect. So in aggregate, the whole system looks the same at the beginning, but because there's little deviations here, you'd end up with something completely different in the end. Although if you at the start measured every position of the particles, sorry, and then you copied that over into a new simulation, that would be exactly the same. The computer would execute all the same instructions in all the same order, and so you'd end up with the exact same thing. Yeah.
This was a good presentation. The neural net.
Yeah.
You've implemented what amounts to a digital filter.
So it's like a series of filters. That's one way of thinking about it. But the filters aren't static. They get adjusted. So I guess one way to think about it, maybe like with the dog example, is that like you can treat this whole thing as like a big filter that like I can hear that. What was I about to say? Yeah, like a filter that magnifies certain parts of the image and ignores other parts of the image, and only takes into account certain parts when it's computing the output. So maybe like in all these images, like the dog or the cat tends to be in the center. Maybe if you look at in aggregate what this whole thing does in the end, is it just looks at the pixels in the center and it says like if it's a certain color, it's a cat, and if it's a certain color, it's a dog. But the beauty of it is that the filter isn't the same every time. Every piece of data that you show the neural network helps it to improve that filter. Sorry if that's like a kind of long-winded explanation. Oh, yeah. Sorry.
Question for you, Max.
Yeah.
Is the consensus of opinion among people working in this field dealing with neural nets that they are accurately modeling what really goes on in our brains, or is there something a little more sophisticated about the actual neural nets that we have hooked up by the billions in our heads? Is it literally as simple as this mathematical model?
So it is a model. So it's definitely not a perfect model. There's things that we know about in the brain that aren't represented in this model. Like in the brain, instead of firing, so in a neural network, there's always going to be an output from a neuron, no matter what you put into it. Whereas in the brain, sometimes you have no output whatsoever. So that's one thing that's not getting accurately modeled here. But there's probably a lot that we don't know about that's not getting modeled. As far as we know, nothing we've built with these neural networks is conscious, and somehow we are. So clearly we're missing something. That's an amazing question.
Yep.
Hold on, actually, let me see your face again. Sorry, I have the slide pulled up. I'm trying to think. There's a few other things that we're not accurately modeling here, but absolutely, yeah, I think we're missing something.
But my thought was that something's going on in the nucleus of each one of those nerve cells that may be a little more sophisticated than is going on in the transistors that's making up the neural net.
Absolutely, yeah. Because what's happening in the computer is that each of these nodes is basically just a math function. Whereas there's probably, as you said, yeah, something much more sophisticated going on inside each cell, probably. Any other questions? Yeah.
Great job, Max. Great presentation and the research project. In your last simulation, so when this loads of the different masses are interacting with each other, are they colliding or they are not? Obviously, they are colliding, but are they becoming like two different masses becoming one bigger masses?
So it's not inelastic collisions. They don't stick together. That would be really, really computationally expensive. You could do it, but it would be hard because you'd have to check basically every particle against every other particle to see if there's any collisions happening and then make them stick together.
Yeah, I think that could be the reason why it did not end up being the black hole. And it
absolutely, yeah. If there was, so this does allow for mass to accumulate in different areas, but it doesn't allow for something like a black hole. I think if you did this in a more accurate way with actual collisions, which is the way that most of these professional simulations are carried out, you would end up with black holes. That's a great question.
Any other questions? Any other questions from online?
One question, Max.
Oh yeah.
You think that if you had enough computational power, that you could make a fairly good simulation of a globular cluster?
I think so. You absolutely can. It depends on like the kind of resolution you want. I think a lot of the main simulations that are being done with like huge amounts of power are cosmological. So it's the scale of like galaxy clusters. And then there's a few that are being done that are like the scale of stars and planets. So you start with a bunch of objects in a disk, but instead of like a galactic disk, it's like a disk of material that forms around a star after it's born, and you can see how planets form. Although I haven't really seen, I'm sure there are like big simulations with globular clusters, but I know you absolutely could.
So Max, what are you doing in the future? What are the next experiments?
So I'll have to see. I'm sort of running up against, with the simulations at least, like the limit of what my laptop can do. But I'm hoping to join some kind of lab in college and continue working that way.
Cool.
Anybody have anything else? Okay, Max, thank you. That
Of course,
was
yeah.
Great.
Thank you.
Yes, Max, great presentation. You always do a great job.
Yes.
Thank you.
And just remind everyone that we're open every Friday night, starting at 7:30, and we give these presentations at 8:30. And with that, wish everyone clear skies.
And Max, have a great, do a great job at Yale. Make us proud.
And for those that
I'll be around.
we're done, George? Great. Okay, great.